Hello, I'm Eric, NQ5Z, and welcome to the Sherman, Texas Emergency Net training on HF and VHF communications. Let's get started. In this session, I'll be covering the following. I will define what spectrum is. I will define the atmospheric terms ionosphere and troposphere. I will explain the various propagation modes for medium frequency, high frequency, and very high frequency bands. And finally, I will give a refresher on the various antenna systems used by amateur radio operators. Spectrum is foundational for employing frequencies in amateur radio. The definition of spectrum follows: the entire range of wavelengths or frequencies of electromagnetic radiation extending from gamma rays to the longest radio waves, including visible light. This includes everything from DC current all the way to sunlight. Next, we will give the definition of ionosphere. The ionosphere is the part of the Earth's atmosphere in which ionization of atmospheric gases affects the propagation of radio waves. The next scientific term we will introduce is the definition of the word troposphere. The troposphere is the lowest, densest part of the Earth's atmosphere in which most weather changes occur, and temperature gradually decreases rapidly with altitude, which extends from the Earth's surface to the bottom of the stratosphere at about 7 miles. Let's spend a moment to understand HF and VHF spectrum and the terms used to understand how it's defined. The term Hertz is named after German physicist Heinrich Rudolf Hertz. He was first to prove the existence of electromagnetic waves. Take a minute to review the terms on this slide. You may have heard hams use the term skip when talking about long-distance HF communications. This technically is the skywave propagation mode. This happens when a transmitted signal leaves the Earth's surface and is reflected by either the F or E layers of the ionosphere. The F layer of the ionosphere is enhanced during periods of sunspot activity. One propagation mode of a special interest to emergency communicators is Near Vertical Incident Skywave, or NVIS. NVIS is accomplished by placing an antenna 1/8 of a wavelength above the ground. The signal is reflected from the ground surface directly up to the ionosphere. For the 75-meter band, that would be 27 feet in the air. For the 40-meter band, that would be 16 feet above the ground. Under ideal communications, you can communicate with stations up to 600 miles away. Now I will introduce the VHF propagation modes, which are line of sight and tropospheric ducting. Under normal conditions, two stations must be able to see each other in order to affect communications. Large metal buildings can reflect or block VHF signals. It is common for airplanes at different parts of an airport to be unable to communicate with each other because the hangars are blocking the signals. Tropospheric ducting is a mode that generates excitement on the VHF and UHF bands. This occurs when there is a temperature inversion in the troposphere. Normally, the air cools as you go up in altitude. With an inversion, the temperature is higher as you increase with altitude. When I lived in the Chicagoland area, I would regularly hear the 145.25 Indianapolis repeater at dawn in the wintertime. The angle of the sun would heat the troposphere for 30 minutes or so. There also have been contacts on 1.2 gigahertz between northern Illinois and Pennsylvania. Ducting can sometimes occur after thunderstorms. The next couple of slides we will be discussing the medium and high frequency bands suitable for regional communications. First up is the 160-meter band. The 160-meter band offers excellent ground wave communications during the day and multi-state communications at night. Digital modes can be an equalizer when compared with stations with high antennas. The only drawback is the antenna sizes make this band hard to operate on. One exception is the magnetic loop antenna, which I will discuss in an upcoming slide. Let's continue our investigation of the lower HF bands with the 75 and 80-meter band. This is the lowest HF band available to radio amateurs. All classes of hams have privileges on the lower portion of 80 meters. It is difficult to use this band during the day as the sun creates atmospheric noise. Range is limited to under 50 miles at best. Where this band shines is at night. As this side of the Earth rotates out of the view of the sun, the D layer of the ionosphere collapses and the band opens up for long-distance communications. One drawback is the atmospheric noise caused by thunderstorms. You can hear lightning crashes from storms a couple hundred miles away. The final band we'll examine is the 40 meter band. 40 is not affected by D-layer absorption like 75 and 80 meters. During the day, you have reliable communications out to 500 miles, and at night you have local communications and communications at distances greater than 2,000 miles. I have workstations in West Texas for my car during the day on 40. Plus, you don't have to wait for sunset for longer distances on 40. You can work out to 1,000 miles in the couple hours preceding sunset. 40 meters would be a reliable band to contact welfare services in Salt Lake City at night. Before I dive into antenna systems, let's talk about polarization, as this can hamper communications within the stake on HF. As illustrated in the graphic, signals are either horizontally or vertically polarized on HF. For Emcomm work, horizontal polarization is recommended. If you're interested in DX, then vertical polarization would be your choice. Why horizontal polarization? Antennas in the horizontal regime are less susceptible to natural and man-made noise, thus improving signal quality. I recommend that we standardize on horizontal polarization, as there is a substantial signal degradation between the two types of polarization. For the final section of my presentation, I will focus on antenna systems. First up is the vertical antenna. While the obvious advantage to the vertical is the 360-degree radiation coverage, this antenna in all actuality is difficult to work with. The greatest challenge is the network of horizontal ground planes. If you were to look at an AM broadcast tower, you would discover a large parcel of land surrounding the antenna. Your first thought would be for safety, as if the tower were to fall, no one would get hurt. While this is a factor, it is not the primary reason. There is a network of ground planes buried underneath the ground, which are in equal length to the height of the antenna. The rule of thumb is the more ground planes, the better. If you were looking for a good DX antenna, the vertical is a good choice. Up next is the most commonly used antenna on the HF bands, the dipole. This antenna is a favorite for its ease of construction and its cost. A dipole is a half wavelength long. The formula to calculate its length is 468 divided by the frequency. The antenna, when mounted at least a quarter wavelength above the ground, is bidirectional. If your antenna runs north to south, your antenna pattern would be east to west. The antenna pattern could hinder communications with certain parts of the stake. We will now direct our attention to the end-fed antenna. I use a random length end-fed antenna because I do not have a good center point for a dipole and I'm space constrained. For a random length end-fed antenna, you need a transformer called an un-un, which means unbalanced to unbalanced. The best kept secret in HF communications is the magnetic loop antenna. They are moderately difficult to construct and can be built between $100 and $300 depending upon the cost of the tunable capacitor. This antenna can be either horizontally or vertically polarized. You could hide this antenna in your backyard and your neighbors and the HOA would never know it. This will be my next antenna project for comms under 5 MHz. While not a good choice for Emcomm, we will briefly discuss the Yagi. This is a directional antenna that focuses the RF energy in a specific direction. These antennas are not practical on a city lot for 40 or 80 meters. This antenna is the DXer's choice for the upper hand bands. Finally, we will discuss the VHF Yagi. What makes this antenna attractive is its ability to communicate over long distances. When horizontally polarized, it looks like an HDTV antenna. Thank you for watching this presentation. If you have any questions, please leave them in the comments and I will do my best to answer. Also in the comments, leave ideas for future trainings. 7-3.